You press record, yeah?
Yeah.
All right, brilliant. So then download it, and then we'll just have to edit it. So yeah. So Nishen, the fourth slide completely, just put a line through it or something. But yeah, we're not doing that. We're just moving on to just what a shaped metal alloy is.
I don't have. I can't. Can someone just delete it quickly? I don't have permission.
Yeah, let me do. It's gone, yeah?
Okay, thank you.
Right. So again, cue me in when you're ready, and then take 5 seconds, and then stop.
Okay, I'm ready. Hello, and welcome to TeamS.A.M presentation of the SpaceBit Hackathon Challenge. We are hoping that by the end of this presentation, you will be able to fully understand the type of mechanism we have created and maybe implement it in future missions.
Hi, I'm Naeem, and I study physics at UCL.
Hi, I'm Nishen, and I study engineering science at Oxford.
Hi, I'm Jiaqi, and I study engineering science at Oxford as well.
Hi, I'm Leila, and I study design engineering at Imperial.
A shape memory alloy is a metal alloy which can be deformed when cold and then elongated when heated. For our lowering mechanism, we will be using nitinol, alloy of nickel and titanium wire. This is widely used in the spacecraft industry, especially in creating light sails. As you can see below in the diagram, when the SMA is cold, it can be deformed to bend, changing from austenite to martensite, and when heated, we can then return the shape into its elongated form, that is back to its austenite straight form.
The design. To minimize weight, we designed a system that doesn't require a deployment box, but ensures a safe delivery of the rover to the surface. The entire system is made up of 2 SMA launch locks that secure the rover to the base of the plate, and 4 cables that uncoil slowly to lower the rover upon landing. The coils are bolted securely to the base plate. The cables consist of 2 nichrome wires for heating and a shape memory alloy wire nitinol SM500. We chose nichrome 5 as our heating element due to its low density and high resistance. There is an outer layer of silicon around the cables to provide protection and insulation. The coils are extremely lightweight and total to just 1.39 grams, with a total length of 1.6 meters each. We calculated the minimum radius of the wires in the cables required to support the weight of the Asagumo rover.
The mechanism. Locking mechanism looks a bit like this. So in the first stage of the deployment process, electricity will be supplied to the nichrome wire wrapping around the SMA element at the bottom of the SMA launch lock to heat it up. This would result in the contraction of the SMA element and the adapter. The Asagumo rover is then unlocked from the lander baseplate. In the second stage of the process, current passing through the coils would heat it up in a short period of time to the transformation temperature, which is 45 degrees Celsius. And as you can see, using shape memory alloys, when we apply heat to it, it elongates and therefore will unclap the hooks and release the deployment box once it has been lowered.
The mass. To figure out the radius of the wire, we consider the force each coil supports and the ultimate tensile strength of the materials. The weight of Asagumo on the moon is about 2.08 newtons, with each of the coil supports 0.52 newtons during the descending process. Since the ultimate tensile strength coils material are larger than 1070 megapascals, we choose the radius of the wire to be 0.13 millimeters in order to hold the payload, and this gives a safety factor of 3. The total resistivity of each coil is approximately 1.0095 ohms. Considering the heat loss due to radiation, coils will be heated up from environmental temperature to transformation temperature in around 8 seconds. The total mass of our design is very small. Each coil weighs approximately 1.78 grams, and the mass of launch logs, brackets, and bolts are about 1.771, 1.127, and 2.139 grams, respectively. In total, the mass of the deployed structure is approximately 39.3 grams. Here are the references we made for the mass calculations. Thank you for watching our video presentation for this year's Making for the Moon Hackathon Challenge. We hope you have gained some valuable information and insights into the mechanisms and ideas we have just presented.
Brilliant, yeah. I think that should work.